So yeah. I'll just, you can go through these, you can do the question. These are the, I'll just tick, okay? Just tick for the homework, sir.
Yeah.
Okay. So just try for this. Let's see if we can understand what is going on here. For the
So which one? 81.
yeah. I thought that I'll give it in the homework, but okay, no, it's okay. I'll just give you a hint. So initially only, what will happen is that K2CO3 will only make it lose one proton. So this will become O minus and nucleophilic substitution first, huh? Okay.
Yeah, sir.
And then second base will remove the second proton and then another.
Yeah.
Okay. Also, one more thing which is instructive actually here is that after it has lost the proton, actually O minus has become here. This O minus is going to attack first this carbon. Why? Because there's a bromine here and there's this C double bond also. There's a lot of pulling of electrons from this due to this group.
Oh, okay. Yeah, sir. Got it.
Yeah. So that is going to be, so ultimately both the protons and both the, I don't want to go to Richter reaction. And the colored compound in this particular case, they've asked. Uh, try this also. I'll just give you the hint that final thing will be like this. I'll call out this group aryl group.
Yeah.
So it will be aryl attached to this carbon atom. And one obviously, one aryl will be here. So let me open this. Yeah. So on this, this I'll draw this complete here. And Okay. This is highly conjugated, so that is why it's highly colored. Actually, we did not study this actually, but I'll come back to this. Huh? I'll show you because this I really like. For example, beta carotene and all that. This gajar is red color and all that because of the extended conjugation. Whenever there is extended conjugation, we get the colored compounds. I'm putting things. Okay, we can do this conversion. Okay. Do this. Okay, do the homework, huh? Okay.
Yeah, yes, sir.
So I'll just put everything on the homework, huh? Okay. But please do it, huh?
Yeah, yes, sir.
Because yeah, I don't want to waste the class.
Yeah.
Okay. But sometimes I feel some questions must be done. So yeah, some questions we have to do in the class, but yeah. Okay, one question let's this do in the propose a mechanism so that you get this. Okay. Try this. Okay. And send it to me. This is the only question we are going to do, and then we are going to move to aldehyde and ketones. See, these mechanistic questions are going to help you because when you are given 3-4 options, you can arrive at the answer. You will have the reactants, right?
Yeah.
And you can, right? You can see if there's one, first there's an acid and so for initial protonation will occur at the OH. Huh?
OH, yeah.
Water will go out. 3-degree carbocation will be formed.
Yes, sir, yeah.
Which will be in resonance.
Oh, okay, yeah. Then
So
with
that
the
will move, and
structure
then
will
the
have launched.
positive will be created here.
Yeah.
And then the nitrogen is here, waiting.
Yeah, then the nitrogen will attack the positive. Yeah,
And
yes.
that plus gets lost, huh?
Yeah. So the
Nice, huh?
double bond is shifting from the resonating structure.
Yes, right?
Yeah, got it. Yes, sir.
Right. So, yeah. Okay. So, I think, yeah. So, aldehyde and ketone and carboxylic acid derivatives. See, initially we talked about this and we said that if Z is more electronegative atom, right? Then what is going to happen? Nucleophilic acyl substitution, right?
Yeah.
But if Z is R or H, then it is the case of aldehyde and ketone, right?
Oh, yeah, yeah, sir.
And this time Z can never go out because R minus and H minus are the strongest bases.
Oh, okay, yeah.
So the general class of reaction of aldehyde and ketones is nucleophilic addition reaction. What we will predict, right?
Yeah, yes, sir.
See,
Because
we will predict nucleophilic addition for both the cases, right? Because how do we predict? We simply look at the delta plus here. So we say, okay, the first word will come from nucleophilic, right?
Yeah.
And there is unsaturation, so addition, right?
Yeah.
So we are predicting nucleophilic addition for both, but we said that in the case of carboxylic acid derivatives, the tetrahedral intermediate can collapse because if the incoming base is stronger, right? Incoming nucleophile is a stronger base, right?
Yeah.
Then it can kick out the Z. But here, whatever the incoming nucleophile, it will always be weaker base because R minus is the strongest base.
Yes, sir. Yeah.
Got it? So nucleophilic addition reaction will take place as predicted by us. Huh?
Yeah.
This is formaldehyde, this is aldehyde, this is ketone. Huh?
Yeah, yes, sir.
Okay. See, this beautiful functional group, vanillin, huh? Vanilla flavoring. See, aldehyde.
Oh, okay. Yes, sir.
Cinnamon, aldehyde.
Yeah.
Camphor, Balaji.
Yeah.
Temple. Spearmint oil, ketone.
Oh, yeah, sir. That one's also ketone calories.
Caraway seed oil. See how nature is. See, nature is the right. See how beautifully it is. This is a coming up, this is coming down, and it has become a spearmint, and this has become caraway seed oil.
Yeah.
Okay, and again, this is progesterone, the female sexual hormone, testosterone, male sexual hormone, and again, you can see the look at the structures. They are right. Everything is same except the groups which are highlighted in the yellow, right?
Yeah.
Okay, progesterone. Okay, now the nomenclature of aldehyde and ketones. Again, what is happening? Methanol, ethanol is the systematic name is right. What we do is where it is here. The final E on the name of the parent hydrocarbon with L. Okay, for the aldehyde, huh? Hence it is called al, huh?
Oh, okay. Yeah.
Yeah.
Yeah, yes, sir.
See, so you look but you did not see, huh?
Yeah.
So there's this Sherlock Holmes story. Suddenly at night, Sherlock they are outing, and Sherlock Holmes is like he asks Watson what has happened, and do you notice something? And Watson says that I noticed the stars and this and that, and then finally Sherlock Holmes says that can't you notice that the tent has been stolen? so so this is Ala. Okay, so the common name of an aldehyde is the same as the common name of the corresponding carboxylic acid, except that aldehyde is substituted for oic acid. So this is for the common name. So this is like formic acid. So instead of oic acid, it is aldehyde. Acetic acid, so right, or ic acid or oic acid will be replaced by aldehyde. Okay,
Okay. Yeah, yes, sir.
you can go through the nomenclature always, and you can come back to me if you want. And this is important. If we have the important, I'll just if we have two aldehyde groups, then it is called hexane diol. See, in this case, E has not been removed. E is removed to avoid two successive vowels. Okay.
Oh,
So,
okay. Yeah,
so
yes.
normally we'll say hexanal, but right, because
Yeah.
right, yeah, got it. So this was asked in I think JEE mains or advanced, so that is why I'm telling you. And if aldehyde group is attached to ring, then the aldehyde is named by adding carbaldehyde. Huh?
Yeah.
Okay, okay, just and then the name of ketones. Okay, replacing the E on the end of the parent hydrocarbon with the on. So if it is propane, then it becomes propanone, 3-hexanone. Okay,
Yeah.
6-methyl 2-heptanone.
Yeah, yes, sir.
Cyclohexanone, 2-4-pentanedione, 4-hexene. You can go through and you can look. Okay, and yeah, I'm just going to go because now I want to arrive at my favorite part. So oh, this is the sweaty feet and armpit. This is the smelling compound. Okay.
Yeah.
This is what she has written here. Anyways, so naming with two functional group. This is the functional group nomenclature, and this is the priority. See, Neha, after teaching us 15 chapters, now she has given this list,
Oh, okay. Yeah, yes, sir.
right? Not in class 11, she,
Yeah.
not in the first chapter
Yeah.
itself, right? She could have done
Yeah.
that, right? Because now we are familiar with a lot of functional groups, right? Got it?
Yeah, yes, sir.
Yeah, you can go through it. It's like you can go through all this. Okay, And this is all this again the mono. Now the real relative reactivity. Okay. See, relative reactivity. Most will be formaldehyde, aldehyde, and ketone. Why? Because the greater the charge on the carbon, right? The more attack will occur here. Here it will be delta plus, delta plus, delta plus. Here it will be delta plus, here it will be delta plus, because two this will
Yeah,
destroy. Only one
providing,
can
yeah.
destroy. No one can destroy the
One
positive
can
charge.
destroy
Huh?
the positive. Yeah, yes, sir.
So electron withdrawing groups will increase the reactivity of the aldehydes, huh? And ketones, right?
Yeah,
If
yes, sir.
R
Because
groups are
it,
the electron withdrawing groups, obviously the positive charge will intensify and the nucleophile will attack faster, right?
yeah, yes, sir.
And electron donating group will decrease the reactivity, right?
Yeah.
Okay. Now, if there will be crowding, the nucleophile will have problem. Traffic jam of Bengaluru, in the last one.
Yeah.
Okay. And the first one, most reactive, okay. Nice
Yeah.
roads of Switzerland, or London, maybe. London is also crowded,
Yeah, yes, sir. So the, oh, okay, yes, sir. Got it. Yeah.
Yeah, yeah, you'll get it. Don't worry. See, and what happens is that after the attack has taken place, right? Because after the nucleophile attacks, we'll get a tetrahedral intermediate.
Yeah.
So initially they are at 120 degree. In the tetrahedral 109.5 degrees. So steric repulsion will be
Yeah.
more. Huh?
Yeah, yes, sir. Yeah, got
Got
it.
it right. So steric repulsion is playing an important role, right?
Yeah.
Okay. Problem 4 you have to do. So I'll just write homework. It's very simple. And see, now the relative reactivities of carbonyl compounds. Okay. Why? Because acyl halide and acid anhydride, because they'll be they're much more reactive, because the positive and everything is there. Okay. And immediately they are followed by aldehyde and ketone, because in ester and carboxylic acid and amide, now what has started happening, the resonating structures have started becoming important, right? In ester and amide. In acyl halide and acid anhydride, they are not very important, so the positive charge is not getting destroyed. Why they are not important in acyl halide? Because the electron donation is coming from 3p, right?
Oh, okay. Yeah, yeah, sir.
So positive charge is not getting destroyed very nicely. Why? But in the acid anhydride, why it is happening? Let us see. Because in acid anhydride, it is like this: OC double bond OR. So although this resonating structure is quite important, because oxygen is getting delocalized here, right? Just like ester and carboxylic acid. But this oxygen will also delocalize on the other side, right?
Yeah.
So the positive charge is on this carbon is not getting destroyed very effectively. Got it?
Okay. Yeah, yes, I got it.
So it will be more reactive. Then there
More
are aldehyde
reactive.
ketone,
Yeah.
then ester and carboxylic acid, then amide are restricted, and obviously carboxylate anion does not react because it is a negatively charged, so nucleophile will not come here. Huh?
So how is ester reactivity though? Oh, because OCHC group will contribute with
Yeah.
I
Only
got
on
it.
one side, right?
Yeah, got it. Yes.
Okay. See how aldehyde and ketones react. So they react like this, huh? Okay. See nucleophilic addition. Zoom, 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 huh?
Yeah.
Yeah, now I feel so happy. If somebody will see this video, they'll say what he is teaching and what is she learning. Huh? Zoom, zoom, zoom. See, so nice. Everybody, we have to kill the competition here. Okay.
Yeah, so in class now I'm getting much more reactions than the others. Even the exam, lots of mechanisms I'm getting than the others.
Right.
Yeah.
See, it's like this is what first go, then you do everything, and then I'll. It's like, don't worry. We'll shock everyone. Huh? That is the aim. Huh? We'll be like that kid, who's playing cricket at 14 years.
Oh,
Huh?
yeah.
Okay, so the aim is my aim is that you will know much more than your teacher. That is my aim. Huh? I think you already know more than me.
Yes, yeah. For the CST rule, he was doing some very complicated thing for
He went
10,
to, I
for
think you
almost,
told me he went as far as to CBSE, huh?
yeah, he made some CBSE test or something like that. For almost 5-10 minutes, he was looking which isomers are going to come.
Oh my God. See, you see, in stereochemistry, what happens is that teachers all over India, they go haywire. Nobody understand what is happening. See, all the clarities, because this she is very clear. The Saraswati who has written this book, okay, she is very
Yeah,
clear, right? How nicely she's like. Look at the presentation, huh? Right?
yeah,
We don't even need to read what she has written. Even the picture speaks thousand words, huh?
yeah.
So nucleophilic addition has taken place, right? So again, Z minus, same thing, Z minus attacks, and this has happened, and right, because, and then finally we give H plus. Now, another one mechanism they have given, nucleophilic addition elimination. We are going to come back to this. Okay, come back. Okay, we'll come back to this because I have so many nice shortcuts that, it's like we don't need anything. Okay, now, first of all, with the carbon nucleophiles, with the Grignard reagent, we know that Grignard reagent is R negative and MgX positive, right?
Yeah, yeah, sir.
Okay. So Grignard reagent is a nucleophile. So nucleophilic addition reaction. So you see what is going to happen. If it reacts with a formaldehyde, we'll get a primary alcohol. If it will with an aldehyde, we get a secondary alcohol, right? See. Ding 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 ding. Nucleophilic addition, nucleophilic addition, nucleophilic addition.
So where is this CH3 CH2 group coming from? I didn't
From
get
which
that.
one?
In
First,
first one, yeah.
see this is the negative, right?
Yeah,
So this has attacked this carbon, right?
yeah.
So actually, this is just like this. She has drawn it like this. It will be CO minus, right?
Oh, okay, got it, yeah.
C and then O minus. Okay.
Yeah, got it, yeah, just alcohol, yeah.
So it will be primary alcohol if it is formaldehyde, because obviously, right?
Yeah.
If it is an aldehyde, then obviously what will happen? Now it will have two alkyl group. The OH, the carbon which is connected to OH will have two alkyl. So it will be secondary alcohol. Huh?
Secondary, yeah.
See, it will be primary, it will be secondary. Got it?
Yeah, yes, I got it.
And finally, if it is a ketone, we'll get a tertiary alcohol. Huh?
Yeah.
We can also react Grignard with carbon dioxide. This is very important reaction. We will get a carboxylic acid, which has one carbon more than the Grignard reagent. Huh?
Oh, okay, yeah, yes, I
Yeah,
got
you
it.
see, everything is now so clear, right? Because we are able to see. Huh? We are not mugging
Yeah.
things, huh? Right? See, that is why the people are there are going doing science, huh? Because they are not blind, and we are mugging up things, huh?
Yeah.
See what is happening here? Nucleophilic addition. Nucleophilic addition. Huh? Okay. Because now we know aldehyde ketones, they undergo nucleophilic addition reaction by. Okay. They are not like our politicians. One day they will undergo nucleophilic addition and the other day nucleophilic substitution, then electrophilic addition. Huh? Okay.
Yeah.
Okay. So nature is like consistent. Huh?
Yeah.
Okay. All this I'm giving you for the homework. Huh? Okay. And now they are talking about stereoisomers also. So when stereoisomers are created, for example, we will see that both top phase, bottom phase, the attack can take place because it is planar. Huh?
Oh, okay, yeah, yes, sir, yeah.
So we'll get both the enantiomers. Huh?
Yeah.
We'll get a racemic mixture. Huh?
Yeah.
Yes. Good. Now, reactions of esters and acyl chlorides with Grignard reagents. Very, very important. This very, very, very important. Why it is important, I'll just come in. So what is going to happen when we react Grignard reagent with this? See, in the first step, obviously the Grignard reagent R negative is going to replace this. Huh? See, because ester will undergo nucleophilic acyl substitution, right? This is an ester. This group will be replaced by the new nucleophile this.
Yeah.
Got it?
Yes, I got it.
And now it has become a ketone. Now another Grignard reagent will come and add.
Yeah, yes, I got it. Yeah.
Right? Nucleophilic addition,
Yeah.
because we just studied the addition of Grignard reagent to aldehyde and ketones. And finally we protonate it. So we are going to get a tertiary alcohol, right?
Yeah.
But these are very special type of tertiary alcohol, because here in these tertiary alcohols, these two alkyl groups will be same. Why? Because two Grignard reagents have added,
Yeah. Yes, I got it.
right?
Yeah.
Okay, they have given this mechanism. Okay, same thing. This attacks, tetrahedral intermediate, it expels. Same mechanisms. Okay. Okay, there's nothing will change. See, first step it has added, we get a tetrahedral intermediate. This kicks back this OH-CH3 group.
Yeah.
Then we get a ketone. Then again this simple. This opens up and nucleophilic addition.
Yeah. Yes, I got it.
Okay. And now same thing is going to happen in the case of acyl chloride. The first Grignard reagent will attack, nucleophilic acyl substitution will take place, then ketone will become form, and ketone will undergo the second addition with Grignard and will again get a tertiary alcohol. In which these two, see, with the yellow she has done.
Yeah. Yes, I got it.
Right? It's the same thing. Just think of
Yeah.
this as ester.
Yeah.
So, yeah. But here comes our favorite reagent, very mild reagent, Gilman reagent, right? It it was able to do nucleophilic substitution with aryl and vinyl halides also, right?
Yeah.
So here what it is doing, it is very mild. It does not attack second time. Okay. Only one group replaced.
Okay. Yeah. Yes, I got it.
Reaction stops. Okay. Okay. Now this is a problem where which of the following tertiary alcohols cannot be prepared by an ester, okay, with excess Grignard. So which tertiary alcohol cannot be prepared, okay, with the with the ester and excess Grignard reagent. And then there is, if you can prepare, then tell us which ester and which Grignard reagent you will use. So we can only prepare those where the two groups are same. So we can prepare this. Because we can bring these two
Oh,
from
okay. Yeah.
Grignard reagent, right?
Grignard reagent. Yeah, got it.
Right? Only those tertiary. So because we know that during the ester and Grignard reagent, if we get, then what will happen? We will, right? The Grignard reagent will come and
Yeah, yeah, sir.
and in the B also we can do, because two alkyl group are same, right?
Yeah, yes, I got it.
In the C also we can do. No, 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 no. We cannot do. All the
Yeah,
alkyl
because
groups are
C,
different.
all are different.
In D we can do.
D we can do, yeah.
In E we cannot.
Cannot do, yeah. D we can do.
F we can do. Huh?
Yeah, yeah, sir.
And D also we can do. Yeah. These, yeah, these we can do.
Yeah, yeah, sir. Got it.
And how we will prepare? So it's very easy to prepare. For example, in this, but in the first one, we know that these are coming from Grignard, right? These methyl groups, right?
Yeah, yeah, sir. In the
So,
all the
so
methyl.
the ester we will choose is 1, 2, 3. This 3 carbon CH3, CH2, C, and double bond OCH3 I can choose. Then I add CH3 MgBr, right?
Yeah.
Excess. And then we protonate it, right? In the end, right?
Yeah, yeah, sir.
Okay. Clear?
Yeah, yes, I got it.
Right? With the first will attack, then the second will attack. Got it?
Yeah.
Now, only in one case, we are going to get secondary alcohols if the ester is this methyl ester format, right? Because now, if RMGX comes, then only two will add and we will get a secondary alcohol, right? Because here there is no alkyl group. Okay, forget it. We'll just come to this in detail. See, if I have a formic acid ester, right? Then what will happen? Huh? It will be like this. Oh, H C double bond O OCH3. Okay. So first RMGX will give me this, right?
Yeah, yeah, sir.
Second, now this is a aldehyde, so this will give me this, right? After protonation, of course, right?
Yeah,
Right?
yeah, yeah, so we'll get two R groups.
Because here we do not have the carbon, right? Else we would have got
Yeah,
tertiary alcohol, right?
yeah, yeah, sir, got it.
Got it? This problem appeared
Yeah,
in
got it
in
now.
1998. Huh? Okay, something like this. But anyway, so this is the now they have asked where we can make with methyl formate and excess grignard. So again, we have to pick only those where two groups are same. Huh? Two groups anyways will be same. Huh?
Oh, okay, yeah, anywhere where two groups are same, yeah. Yeah, D also.
Right? Got it?
Yeah.
Homework. Just put this with this homework. Huh? Okay. Predicting product of reaction with Grignard reagent. And this is a very popular question. What will happen if we use the Grignard, if we treat the Grignard reagent with carboxylic acid? The Grignard reagent will be destroyed. It will pick the proton and become an alkane. Huh? It will not react. R negative will not react here because it is such a
Yeah.
strong. It is the strongest base, right? R negative is the strongest base. It will immediately pick the proton. We talked about this, that Grignard reagents cannot be prepared where there are acidic groups, right?
Yeah.
You're getting it?
Oh, okay, yeah, yeah, sir, yeah, got it now.
Right? Because it's the
Yeah,
strongest base.
yeah,
It does not care about the attack. It will immediately pick the proton and run away. Huh?
yeah, like because it's acidic, yeah.
Right? Because its name is acid. Huh?
Yeah,
Okay. It is not acidic. It is acid. Carboxylic acid. Huh? Okay.
yeah, got it, yeah, sir.
Which of the following compound does not form an alcohol when it reacts with the Grignard reagent? Huh? Okay. Then I'll So you tell me, we'll do this quickly in the 11th. So if there is an acidic hydrogen, right,
Yeah.
then Grignard reagent will not be able to attack. So in this, Grignard will pick this proton and will be destroyed, right? Because here the proton is attached to nitrogen, right? So it is an acidic proton, right?
Oh, okay, yeah, yeah, sir, got it.
Here we'll get an alcohol.
Yeah,
Here
here,
again, this H will be picked.
this
So,
H will be, yeah, the acidic one.
right?
Yeah,
So here we won't be able to get the alcohol, right? In the C, right? Grignard will not attack the ester, right?
yeah,
Because it will just pick the proton and destroy itself, right? Got it?
yeah, sir, got it.
Clear? If you want to ask something, you can always ask.
No, sir, got it. Clear now, yeah.
Okay, okay. You see, clarity is most important, huh? Okay. You don't have to agree with me.
No, sir, yeah, got it.
Okay, now it's again the retrosynthetic analysis. Suppose we want to synthesize with this, then we are thinking backwards. Okay, this can come from by oxidizing this alcohol, and this we can get by this combination, because I can use the Grignard reagent and the aldehyde.
Yeah, sir, yeah.
This aldehyde can come from this, and this can come from this. So now in the forward direction, we can synthesize it like this. So this is again homework. I'm just giving you a lot of homework. We'll discuss this maybe in the class, okay, so that we We spend less time here. Huh? Got it?
Yeah.
Okay. We'll discuss this, but anyways. So be ready with the homework with the carboxylic acid derivatives. First, we'll discuss in the next class. And then
Yeah,
if
yes,
you're ready
sir.
with this, then we'll also discuss. Reaction with acetylide ions, we don't care. These are also nucleophiles. Nucleophilic addition is taking place.
Oh, okay, yeah, yeah, sir. Yeah.
Right? This is just a fancy proton source, huh? H plus. Okay. This is just to give the H plus. And we normally write H plus. Here it is, that's the same thing. Okay.
Yes, sir, got it.
It is there to give the H plus. So this O minus, this O minus is picking this proton and this. Okay, now this is the homework again. Okay, just use this homework. Cyanide ion, we don't care. It is just a nucleophile. Huh? See, Cn minus attacks. See the mechanism also down. Huh? Everywhere we protonate this, O minus at the end, in the nucleophilic, in the aldehyde ketones. Got it?
Yeah.
See? Okay?
Yes, sir, got it.
See, what they are saying is that HCN has pK of 9.14. So Cn minus is a relatively weak base. So it can be expelled from the tetrahedral intermediate. So we must, so we cannot use just NaCN to get cyanohydrin. We must use NaCN and HCl. Okay. We must protonate it. Huh? Because Cn minus is a weaker base. Okay. In the
Yes,
case of
yeah.
this, all this is pK 60. All these are very very strong bases, right? But the conjugate of HCN is Cn minus, which is will be a weaker base, so it can be eliminated from the addition product. So so just after addition of Cn minus, this is not stable. See, this is why the equilibrium is written here. Huh? Okay, it can go back. Okay,
So why will it go back?
because this can come back and it's a weak base.
Oh, okay.
Okay, so we must protonate it. That's what they are saying. And this is called a cyanohydrin. The on the same carbon you have Cn and OH. Huh?
Oh, okay, yeah. Yeah, sir, yeah, got it.
And see, okay. So yeah, do this also. See, we cannot prepare a cyanohydrin by sodium cyanide, right? Because it will not be protonated, right?
Yeah, yes, sir.
All these are homework. Why aldehyde and ketone react with a weak acid but do not react with other than. If they are protonated, Cl minus will be so weak that it will not attack them. It will not act as a nucleophile. That is why, okay, in 17. Huh? it cannot be that weak that a base so that it does not act as a nucleophile. Huh? Cl minus HCl is so strong acid and Cl minus is very, 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 very weak. It is not interested in becoming a nucleophile. Okay. HCN is relatively still weaker, right? Because it is pK is 9.15. The pK of HCl is less than 0. Huh?
Yeah, sir.
Okay. So HCl is very, very strong acid as compared to HCN. So Cl minus is very, very weak base. Huh? Okay.
Yes, sir. Yeah, got it.
See, cyanohydrin. CN, we hydrolyze CN, we get COH. So nice. Huh?
Oh, okay, yeah.
We can also reduce this just like a triple bond. Huh? H, 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 H.
Oh, okay, yeah, sir.
See?
Then we can treat as CNP.
Yeah. Huh? Got it?
Yeah.
Okay, these are problem solved and unsolved. So you have to, this is homework. Reaction of carbonyl compound with the hydride, and we are not interested in anything. We just know that they will undergo nucleophilic addition reaction. See, now here then what is the nucleophile here? Nucleophile is H negative. Huh? Okay, sodium borohydride is a source of H negative. So H negative will come, it will open up and it will become OH. Okay, same thing is here. Yes.
Yeah, sir. Yeah, just going through it.
Okay.
Oh, okay, yeah. So we're just adding H minus.
Because it is nucleophilic addition.
Yeah.
Okay, it is not the Bengaluru CMPM. Huh? Who will
Yeah.
change? It will remain nucleophilic addition, right?
Yeah.
Else I will be like your teacher. Huh? I will tell you CBSC and CSC. Huh? ICSC
Yeah.
also. Okay. So it will remain same. Huh? And it's a fancy mechanism which we don't need. I just showed you. You can just add H negative. Huh? Okay. It's the same thing. It's a BH4 minus is just the source of H negative. So this is H negative going here. H is added here and then protonate. Huh?
Yes, sir. Yeah, got it.
Homework. Huh? Acyl chloride with hydride ion. See, the same thing will happen. First, H negative will replace this. Huh? See, here we'll have a right. Huh? Cl has been replaced by H. Huh?
Yeah.
I just use the green because they have used the red. So this is acyl. See how I'm thinking. Acyl chloride, nucleophilic acyl substitution. Where is the nucleophile which will replace the Cl? I know it will be H minus. So I will put an H here. See the product. Right?
Yes, sir. Yeah.
Got it? Because the general class of reaction of acyl chloride is what? It is nucleophilic acyl substitution, right?
Yeah,
Yes or
yes, sir.
no?
Yeah, got it. Yeah.
Okay. For
Yeah.
the carboxylic acid derivatives, it is nucleophilic acyl substitution, right?
Yeah.
And now after first addition, we have got an aldehyde. It will undergo nucleophilic addition reaction.
Uh, okay, yeah, sir. Yeah, got it. Same reaction.
Okay, yes, same
Yeah,
thing,
same thing.
same thing,
Yeah.
Sarji. Okay. Right?
Yeah, same thing. Just Cl is
It
get
will
like,
always be
yeah.
same thing, Neha. Because it will be nucleophilic addition, right?
Yeah.
That is their general class of reaction. Huh? Where will the Muslim go to pray? In India, he will go to a mosque. And where he will go? In Dubai, to a mosque.
Yeah.
To in the USA, to a church? No. The same here, the same functional group, right?
Yeah.
Nucleophilic addition, right? Okay.
Yeah, sir. Yeah.
Okay, we'll move forward. Now here, this is a very fancy thing, and we have to remember. See, lithium aluminum tri. This is tri-tertiary butoxy aluminum hydride. Huh? This is a very there it is. Yes. only one reaction has stopped at aldehyde state. Why? Because here only one H negative is available. Huh? So it will just replace it once and stop. Okay. So it is very less reactive as compared to NaBH4. Huh? Lithium aluminum hydride is a stronger reducing agent than sodium borohydride. However, replacing 3 of the hydrogen of lithium with OR groups make it a weaker reducing agent than sodium borohydride. So it reduces an acyl chloride only as far as an aldehyde. You can remember it like this, that only one H is present here. So its reaction will stop only after substituting one hydrogen. Nucleophilic acyl substitution, Cl will be replaced by one hydride ion, right?
Yeah. Yes, I got it.
Reactions of an ester with hydride ion. Oh, ester. Same drama. See, first this H negative. I know. See how I am looking. Oh, ester nucleophilic acyl substitution. What is the nucleophile? H negative. So I will replace this group by an H. I will get this product. Huh?
Yeah, got it. Yeah.
Same thing. Same thing. Huh?
Same
Okay.
reaction. Yeah.
And after aldehyde addition, huh?
Yeah, I got it.
Because everything will happen. This is also very important reaction. So here only one hydrogen is present. So in the presence of diisobutyl aluminum hydride, which is commonly known as dival-H, what will happen? That only this will attack, and only one H will attack. For example, see this diisobutyl aluminum hydride dival has been used. See, only one H has been replaced. Huh? This is the way I've remembered. So I'm telling you, whenever there's only one H, so the reaction will stop only after substituting one H here.
Yeah.
Okay. Got it?
Yes, I got it.
Reactions of carboxylic acid with hydride ion, you can see it through the mechanism. Mechanism is a very different mechanism it will be. But here is my shortcut. Obviously the mechanism will be different because H negative will first of all pick this proton, right? Because it is the strongest base, so it has to react.
Yeah.
But my shortcut is this, that I know that nucleophilic acyl substitution. So in the first step, I just do a shortcut. I just replace this by OH by H, then this become aldehyde, and again H negative add, just like usual. Okay. And I give this product. Okay. This is, I'm just telling you to form the products fast. Okay.
Okay, yeah, yes, I got it.
Okay.
Like the previous one, yeah.
Right. Yeah. But obviously the mechanism will be different because first of all, H negative will pick the proton, and then this thing will happen. More or less, we'll get the same product. Okay. The mechanism is just fancy. So this mechanism will not serve as much as it should serve us. So we don't really need to this, but read if you want to. But I've put a cross here. Okay. You can just think it like as I've shown you. Okay.
Yes, sir, yeah.
Because it will be faster, and we just need the products, right? Okay.
Yeah.
And everything is logical. We know it is nucleophilic acyl substitution and everything. Okay. Again, yeah, this is homework. Okay. Now, amide with hydride ion. Where's the mechanism? See, this a very this peda mechanism. Huh? So how do we do it? Well, for me, see, you can go through the mechanism, but again, mechanism will not. I mean, see the use of the mechanism when it is serving us the purpose also. And here you can go at once, but see for amide, how do I do? I'll tell you that. For amides, I will just first of all, amides are very unreactive, so only lithium aluminum hydride will work. Sodium borohydride will not work. NaBH4 will not work here. Okay. Lithium aluminum hydride will work only.
So I
And
won't NAD. Oh, okay, because LiL
it
is
is
going
weaker.
better.
Sodium borohydride is weaker. And lithium is obviously more reactive.
Yeah.
Okay. So now what is happening here? First of all, C double bond over here. So what I do is I simply replace this double bond over by two hydrogens. That's it. Okay. That is how we draw the product for the reduction of the amides, and we will get the corresponding amines. Okay.
Yeah.
Got it?
Yes, sir. Got it.
First two are okay, but this is powerful. This is powerful. See? Quite a change, huh?
Yeah.
The other are still okay, but this like, ooh. Tertiary amine cyclic. Okay, here's the mechanism. You can go through if you want, but like I told you, it won't serve you, so you just go through this. Where are the problems for this? The next. Yeah. So here we are, and yeah, in the next class we'll discuss. Mm. So more about reduction reactions. Now, yeah, this is also important. See, they are saying that you can think of H2 as H minus H plus or H dot H dot, or like this, 2 protons and 2 electrons. Huh?
So what's happening in the last case? Oh, okay. Okay, got it. Got it. Yeah.
They have even separated the H dot as H plus and single electron. That's it. Right?
Yeah.
Right. This H dot is nothing but H plus and 1 electron. Huh? So this is H dot. This is also H dot. Huh? Right?
Yeah.
So 2 electrons. So now see. So this will occur. This will happen. But here there will be no reaction. Can you tell me why? Both are nucleophiles. Both are nucleophiles. Alkenes and alkynes are
Oh, okay.
nucleophile. They react with electrophiles. NaBH4 and lithium aluminum hydride will give H negative. Negative, negative, attract, huh?
Yeah.
Negative, negative, attract.
No, sir. Yeah.
Repel. Okay, so that is why no
Yeah.
reaction, huh? Right? This is
Yeah.
also nucleophile, right?
Yeah, so both are nucleophiles, so they won't react.
Right? This is also nucleophile, right? Got it? No reaction. Understood?
Yeah,
Got
so
it?
understood.
So sodium borohydride, these can only reduce those things where their carbon is carrying a delta positive, right? Right?
Yeah, sir. Yeah.
Okay. Reduction by 2 hydrogen atoms. Okay, let's see what they are saying here. Yeah, this we know. Okay. Hydrogenation is working everywhere, even in the case of where the delta pluses are there. See, for this is a very powerful thing. Catalytic surface and triple bond and double, everything it will be reducing. Nice. It is because catalytic hydrogenation is working everywhere. Right? It is just concerned with the unsaturation.
Okay. Yeah. Yeah, sir.
Right? Just treat these also as double bonds, normal double bond, normal triple bond, just like these. Hmm?
Yeah. The
Unsaturation add
normal
HHHH.
addition. Yeah. So this will also be consider addition, right?
Yes.
Okay.
Okay.
Yeah. Yeah, sir.
Because they will pick up from the catalytic surface, right?
Yeah.
Right? Same thing, same thing. See, these are also working. Same thing, HHH, right? Unsaturation. One H here, one H there.
Oh, okay. Yeah.
Okay, where it is. Okay. Okay, what are the products of the following reactions? Yeah, you can do this. Reduction by addition of electron, proton, and see, in the presence of sodium and liquid ammonia, we are getting trans butene. Huh? We did this, I think, in the alkyne. Huh?
Yeah.
Okay. Oh, these are very important. See, now what is happening? Chemoselective reaction. So if I have sodium borohydride will not react with esters because esters are less reactive as compared to ketones. So if I am using sodium borohydride, then only what will happen? Only the ketone group will get reduced, not the ester group. Huh?
So why won't the ester get ready? Oh,
Because
because
because it is much less reactive. So we need a powerful reducing agent like lithium aluminum hydride to reduce the esters. Sodium borohydride is a much weaker as compared to lithium aluminum hydride, so it is not able to do the reaction. In the case of ketones and esters, ketones are more reactive towards nucleophilic acid substitution, right? We saw that order, right?
yeah.
Okay. So ketone is getting reduced in preference to this. Just wait, you'll understand. Now we have a triple bond and a double bond. So obviously we know in the presence of sodium and liquid ammonia, we'll get a transalkene. So if you see it carefully, they have drawn a transalkene. Huh? This is a trans. Huh? See, opposite H. Huh?
Yeah.
Okay. So in the exam, they can also give you this option. Huh? They'll draw everything and they will draw C, H, H. Got it? Then this will be incorrect. Huh? Right? Because it is cis. Huh?
Oh, okay, yeah. Yeah.
That is why I drew it. Right? Okay. See? We have to see that in the case of alkynes, we get trans, right? When we use sodium and liquid ammonia. Go back to alkynes and check. Okay. Okay.
Yeah, yeah, sir.
See what is happening here. First, sodium will give an one electron. We'll get a radical anion. This will pick up proton. Then second sodium will give an, and now this will be trans, right? This vinylic anion is trans, huh? Like this I've drawn. Because the methyl wants to be as far as possible, okay? And now the proton will be picked, so we get a trans alkene, okay? So when we reduce an alkyne with this sodium or liquid ammonia, we get a trans alkene, okay?
Yeah.
Okay?
Yeah, yeah, sir. They've done this in alkenes, yeah.
Yeah, we have done this. But now here, see, sodium borohydride, obviously NaBH4 will not attack the double bond, right? Because it is negative. NaBH4 is H negative. Alkene is also a nucleophile. Both are negative, right? Nucleophile N for nucleophile, N for negative, right?
Yeah.
So where will H minus attack? Only the carbonyl part, right? Ask.
Yeah, sir. Just going through it then.
Yeah.
Oh, okay, got it. Yeah, sir. Yeah. Yeah, clear now. Got it.
There's a lot of work now. Do all the homework. Okay.
So start from this chapter, right?
You have done the carboxylic acid derivatives homework?
Yeah. I think I have few questions left from last class, but I think other than that, I'm done.
Okay. Yeah. Finish everything. Finish those first. Huh?
Yeah.
Sequence. Do not break the sequence. Okay. So now I will show you something else. So if we have nitrogen and oxygen nucleophiles, okay, then what happens is something which we call nucleophilic addition elimination mechanism. So first the normal nucleophilic addition reaction happens, what we expect, okay, and you can see that they have given trace acid. So after that, this trace acid is going to proton, because we are always getting OH, after adding any nucleophile to the aldehyde, we are getting OH. So what will happen? That OH will get protonated and water comes out. Forget everything what I have said. Just see how we will draw the product. Huh? So if I have any aldehyde and ketone, C double bond O, okay. So what I will do, if I have anything H2N and any group here, any general, I will simply take out the water. Okay. And what will I get? This. Got it?
Yes, I got it.
Now see the products. If you can understand. Go through them. And let me know when you're done, so that I can scroll down.
So what exactly is a trace acid doing here?
Very little acid. We'll come to this also. First, just focus on if you can make the product. For example, in the first case, I can place this like this, right? H2N CH2 CH3. Yeah? And we get the product. Huh?
Okay, yeah, yes, I got it.
Similarly, I can place this R H2N CH2, and I'm writing this as phenyl. Huh? No, I'll use the different color. Oh,
So
where did it go?
removing water from everything.
Sorry?
By just removing water from
Yes. This is my super technique. Right?
Yeah, got it.
Okay. You'll see how important and how good they are, we'll see the mechanism also, but just see. Now see the product. Huh? Huh? Same thing, huh?
Yeah, same thing, just removing the water.
Yeah. Right? Now the mechanism is going to come. Okay. The big drama they're saying. Okay, we'll just skip for the time. So how the mechanism is happening? You see, the first step is obviously this is the nucleophilic addition, huh? First step.
Yeah.
And first step, and the protonation occurs, and the tetrahedral intermediate always loses the proton, right?
Yeah.
Whenever
Yeah.
nitrogen, oxygen will have positive, they'll remove the proton. Now what happens, Neha, is that this OH gets protonated, okay? And it becomes OH2 plus. And since nitrogen has lone pair, it pushes it outside. See, zoom, and the water goes out. And as the water goes out, this nitrogen gets positive charge. It has one more hydrogen, so it loses that hydrogen, and we get this imine. Okay, so you can go through the mechanism as a homework, but again, it will not serve you any purpose, because in the end, we now know a very short method to get the products, right?
Oh, okay. Yeah, yes, I got it. We can just remove the water from
Yes,
that. Yeah.
right. Okay.
Yes, got it.
Yeah. So that is how it is happening. Okay. Now this is very important. So now what is happening is that we have to control the pH. pH is around 4.5 here. Okay. Weakly acidic. Why? Because if we use very strongly acidic conditions, then amines are bases and it will get protonated and then it cannot act as a nucleophile.
So I didn't get that point.
If RNH, if we are using strongly acidic conditions, RNH2 is a base, right?
Okay, yeah,
Amines
so
are
just get
bases, right?
protonated
Nitrogen. So it
immediately.
will react with H plus and this will become this. And so now it cannot act as a nucleophile because there is no more lone pair,
No more balloon pairs left, yeah.
right?
Yes,
So,
I got
so we
it.
have
That's
to,
why only trace
yes,
acid.
yes. So this is the pH rate profile. You know, what is happening here is like, see, as if
So
we
like
decrease,
any trace
if
acid
the
actually,
pH is
so
very less, means the conditions are very acidic, then what is happening? Then obviously the rate will fall, right? Because the nucleophile is not there to react, right? Because pH is
yeah.
very, right? So
So trace acid as in any weak acids will
yes,
happen.
yes, yes, yes.
Okay,
So
got it.
see the around 4.5, which is the pH of acetic acid, right? Oh my God, what is happening here? So here we are getting the maximum rate,
Yeah.
right? And again, if we make it very basic, then what will happen? If we make it very basic, then this will not get protonated, right? Because then only it will convert into a good leaving group and nitrogen will be able to push it, right?
Yes, yeah.
Right? So, yeah. So we have to hit a sweet spot. We have to balance it. Okay, okay. So this question appeared in IIT. So, yeah. Imine hydrolysis. So, what will happen? If we have this, if we hydrolyze it, how we will hydrolyze it? See, hydrolysis is simply that we have to give water and that, right? So I'll break it like this. Okay, first thing. And I'm hydrolyzing it. So H plus and OH minus. So this is delta plus and this is delta minus. So this will get H plus, right? And this will get HO minus, right?
Yeah.
Since I'm breaking two bonds, so I will get C2OH like this. 2OH will be there and RR is there. And this will get CH3, CH2, NH2. Huh? This nitrogen will get two hydrogens. Huh?
Oh, okay, yeah, got it.
Two bonds. Huh? HO
Yeah.
minus, H plus. Got it?
Yes, I got it.
Now, whenever the carbon has two OH, it will immediately lose water. Okay. It will collapse back and we'll get the corresponding this ketone.
Okay, yeah, yes, I got it.
Since the medium is acidic, the amine will not be free amine, it will be protonated. Okay.
Yes, yeah, got it.
Now this reaction is not reversible because the amine cannot act as a nucleophile. Okay. Right. This
Oh,
reaction is
okay,
not
yeah, because
reversible
it's
because
fully
now
protonated.
this cannot act as a nucleophile. Huh?
Yeah.
Okay. Homework. Yeah, yeah. Now we'll come to this. Obviously, homework. So I'll just come to this and I'll show you. See how they will ask. So they will ask you that, acetone and this benzo acetophenone is treated. They are both treated with, say, hydroxy element, H2NOH. See, okay. So how many products we'll get? So we'll immediately draw it like this and see NOH. Oh my God, this will not. This is not a simple thing. See, cis trans here also will be there, but here no cis trans because this sp2 has both the group same. But on the below one, we will have an OH, this lone pair, PHCH3, where PH and OH are on the same side, and then we will also have here OH and CH3 will be on the same side. Got it?
Yeah.
So actually we'll get 3 products including stereoisomers, but normal people will draw 2 products, huh?
Yeah.
Got it? So this is what they have said, that hey, dudes, if they have the different alkyl group, the oxines are imines and oxines, they are going to occur as cis and trans. Homework. Okay? Got it?
Yes, yeah, got it.
Reactions with secondary amines. Okay. Now secondary amines, I'll just go. See. I'll just stop. Okay, because I've given time to someone, but after a while I'll stop 6:30. But I think that is sufficient. I won't make up for this 15 minutes because we have already done so much, right?
Yeah, yes, yeah.
Okay, please don't ask for this. Okay, we are like see how speedy we are now, right? Right. This will take the, when in the school you'll see how long it will take. Huh?
Yeah, yes, so that's no longer, yeah.
Right? They're taking weeks and like that, right? I mean, it takes a lot of time, right? Because they just don't know what you have to teach and right. Because we worked so much on the curved arrows, that is why.
Yeah.
Now we are talk. I'm going to talk about what will happen if the secondary. See, in the primary amine case, this carbonyl group was there, and this was primary amine. So water could easily be taken out, huh? Right? Yes.
Oh, yeah, yeah, sir.
Right. But if I have a ketone or aldehyde, and I have a secondary amine.
Yeah,
Secondary
then
amine
you
means
don't
this
have two hydrogens, yeah.
2 alkyl groups, right?
Yeah. So here
Now we
we
cannot
can't
take
take
out the
out
water, huh?
water. Yeah.
Okay. So let's take this example. Huh? And somebody asked me, "Hey, dude, what is the product for this? Huh? You are so super champion." For let's make it more complicated. Hmm. NH, huh? See, and trace acid, obviously. So, if you remember, your sir must have taught you ketoenol tautomerism.
No, sir, not yet.
They have something called enol, we have heard, right? In the
Yes, sir, yeah.
during the alkyne.
Alkyne chapter, yeah.
So this hydrogen immediately will draw this enol.
Yeah, and become double bond and OH.
Okay.
Yeah.
Yeah, see. Can you see now what we are doing? Huh? What are we doing here?
Oh, okay, yeah, yeah, sir. Tautomerize to get water.
Yes. Okay. Okay. So in Bangalore, we should tautomerize, huh? Because the water problem will be solved. See, huh?
Yeah.
This is called enamina. En from alkene and amine from this. So the same carbon has nitrogen and double bond.
Yeah.
Okay. So this is how we draw the case, draw the products for secondary amines. Okay.
Yeah.
And there's a mechanism also, you can go through it, but see.
So it's same thing as the water, but just with one more step of tautomerism.
Yeah. Because we don't have two hydrogens there, huh? Right?
Yeah.
Right?
Yeah, yeah, sir.
You know? And here's the mechanism like this will happen, that will happen, protonate will be lost, and now finally we see, after pushing out, what is happening actually is this. After pushing out, the nitrogen does not have any more hydrogen here. See, because it's a secondary amine. It has already lost its hydrogen after the first step. Okay. See, let's go through the mechanism. What has happened? First, the initial attack has taken place. Okay. And this protonate and everything is nice. And now nitrogen has positive charge. So it can lose its proton to stabilize itself. This is what happens, right?
Yeah.
Okay. Till here it is clear. But now this protonation has occurred. Okay. In the primary amine, we still have one more hydrogen here, but it's the secondary amine, so we do not have anything. So after protonation, okay, it protonates and it obviously kicks it out because it has the lone pair. But after kicking it out, it has positive charge and it does not have any hydrogen. So what is happening? We are getting, so this alpha hydrogen is getting picked up. Okay. So this gets lost and this positive gets stabilized. So we get an enamine. So we get a double bond with that as well. Because the
Oh,
nitrogen must
yes, sir.
stabilize itself, right? It has
Yeah.
positive charge. Right? So
It's a
that is
positive
what has
will
happened.
go there, yeah.
Okay. And so we have this shortcut where, see, this shortcut will be so useful to you.
Yeah, so much more than this mechanism, yeah. Sir, I'm not able to hear you.
I'm not speaking.
Okay.
Yeah, I'm just looking at this like. Okie dokie. We can also hydrolyze it back. Okay, I want you to tell me how the products will be formed as a shortcut. The same thing. Let us break things from here, and the nitrogen will get H plus, and this will get the OH.
OH, yeah, then I'll tautomerize the ketone.
Yeah, see, now
Yeah.
you don't need me. Huh? Okay.
Then last one, that H plus will just
Yes, because it is acidic, right?
acidic medium, yeah.
Right. So these are homework. Huh? We have done a lot, I think, for today. But yeah, so happy. Reductive ammunition. I'm tired. It's like it's okay. Now it's like I'm done. Okay. We're done. We have done a lot of portion now. It's more than
Yeah.
sufficient. Okay. This chapter will be ending soon. Okay. Because we have, this is a very, very decently long chapter, but we have covered almost everything. Huh? Because I think it'll end somewhere. Yeah, it's a decently long. It has ended here. But yeah, we have covered a lot actually. Okay. Covered more than half of it, and it's the most important chapter first of all, and it is I mean, it is the chapter where a lot of people have a lot of problems, but do all the problems because now you have a lot of work. Okay. Hello.
Yeah, sir.
Okay, you have a lot of work now. Okay, a lot of questions you have to do because problems are going to make you. Okay, problem solving.
Yeah.
Okay, so I want, so in the next classes we will be discussing first the problems of carboxylic acid derivatives and aldehyde and ketones. Okay.
Okay, yeah, sir.
And yeah, I'll also upload it. Huh? Okay.
Yeah.
Okay. You are watching the videos?
Yes, yeah, wherever I have a doubt, I'm watching it.
Okay.
Properly.
Yeah, that is also helpful, right? Whatever we have covered, right?
Yeah.
Yeah. Cool. So I've made a separate playlist for you. Okay. Okay, nice. Huh? We'll meet soon. Huh? Okay. If you have anything, any doubt, you can also ask me through WhatsApp. Huh?
Yeah, sir.
Okay, Naya. Take care. Okay, and blast the teachers and everybody. Huh?
Yeah.
Chalo. Okay. Bye. Bye. Bye.
Thank you, sir.